All right, at long last, let's actually solve this problem. So in the last video, we set up the Lagrangian. We set it up as a sum of infinite Lagrangians. Each, we call it t, and then at each time t plus s, we have to solve this other Lagrangian. So we'll define that L sub s is going to be this. It's just the Lagrangian at time t plus s. And we just noted by looking at what variables are present at every time that the only two times that are relevant are s equals 0 and s equals 1. So we just have to worry about these two. So our problem of solving infinite things reduces to just solving two things, 0 and 1, and we just have to add them together. So let's do it. Let's solve. Let's take the derivative. Let's take the derivative of LT with respect to CT and set it equal to 0. Okay, so pause the video and get that answer if you don't already have it. If you do already have it, let's go through it right now. So when we have to look at when s equals 0. When s equals 0, we have a CT here, we have a CT here. Okay, and that's all. And when s equals 1, the only other case we care about, we do not have a CT here, we have a CT plus 1, we have a CT plus 1 here. Yeah, we don't have anything, so we only need to look at the 0 case here. So when L equals 0, let's take the derivative. This will be CT to the 1 minus C. Beta will be gone because beta 0 equals 1. So we'll have CT. Let me write down the relevant pieces. So I'm going to copy, I'm just copying the Lagrangian at s equals 0, and I'm only copying the pieces that will not have a derivative of 0. So this goes to 0. We're going to have something out of this. Indeed, we're going to have CT plus s. Whoops, we're at 0. So we're going to have a CT here. We're going to have a KT. No, we're not. Let's just multiply this PT through. Yeah, so we're going to just have this times PT times CT, and that's it. Okay, this is our Lagrangian. That's all we need to worry about. So we're going to take the derivative of this with respect to CT. Okay, and we're going to get power rule, bring this down. Those will cancel, and we'll be left with minus sigma c. So CT minus sigma c minus lambda t. I wrote t plus s here, I'm sorry. PT equals 0. Okay, so this is our first order condition. We can solve for lambda. I should say that you shouldn't leave lambda floating around in your first order conditions, okay? We want to eliminate that. So let's solve for lambda just by bringing this over to the left. So we'll get lambda t pt is equal to ct to the minus sigma c, and then lambda t is equal to ct minus sigma c over pt. Okay, and this is our first, it's not really a box yet because we need to put it together with the supply function. This could be your first box. Okay, let's write that over here maybe. I'll make a little solutions area. And our first solution is going to be that lambda t is equal to ct to the minus sigma c divided by pt. Okay, let's get rid of this, and then let's take the derivative with respect to LT. So please pause the video and solve for the derivative of LT, script LT, with respect to labor. Set it equal to 0 and give me a computation. Okay, find in these terms, when s equals 0, what do we care about? When s equals 1, what do we care about? And then make a smaller expression and take the derivative. Pause. Have tried. Come back. Okay, you tried. Welcome back. Let's write down what we care about. So when s equals 0, there's an LT right here. So we're going to have minus LT. I'm doing the same thing. I'm first copying down the Lagrangian. I'm not taking the derivative yet. I'm just copying down the bits that we care about. Okay, so there's no LT inside of this first part, but there is an LT over here. We're going to have minus times minus is going to be plus. So we're going to have plus lambda t, because we're at time s equals 0, WT LT. And there's no other LTs. Now we need to check when s equals 1. We know that that matters sometimes, but it doesn't matter for LT because there's no LT in time s equals 1. So we just need to take this expression and get partial LT. So we take the derivative. Again, we have the power rule. This power comes down. This guy comes down here. And so they'll cancel, and we'll just be left with sigma L. So we'll have minus LT sigma L plus, and then this will just go to 1. So we'll get lambda t wt equals 0. And we can put the LT, I guess, to the other side. We can write, or we can solve for lambda, why not? So we'll get that lambda t is equal to LT sigma L divided by WT. So we can add that up to our box. We have a second solution for lambda. We have lambda t is equal to LT sigma L divided by WT. Perfect. Okay, and so the last thing we need to do in this video is to get the derivative with respect to KT. Okay, so we need to take partial Lagrangian partial KT, set that equal to 0. So do the same thing, go step through this one looking for KTs, and then step through the S equals 1 part and look for KTs, okay? Pause the video and have a try. Okay, welcome back. Let's do the same thing. I will not take the derivative. I'm just going to copy down the parts of L0 and L1 that we need to worry about when we take the derivative to make things organized. So there's nothing here, there's nothing here. And there's some stuff with lambda. So let's start with minus lambda t and t plus s. So there's a kt here. So we're going to have kt, pt kt, because this kt is multiplied by this pt, right? Now this is t minus 1 right now. We're in s equals 0. So s t plus 0 minus 1 is t minus 1. We don't look at this one yet. And same thing here. We don't look at this one yet. Okay, so this is everything we have in the first bit. So now we need to go to s equals 1. And when s equals 1, we have a beta, because we have beta s out front. So we're going to have plus beta. Okay, we still have nothing here. We have a minus lambda t plus 1. We have a kt plus 1 here, but we don't care about that. We're doing kt. So we have a kt plus 1. We have a kt here, because t plus 1 minus 1 is kt. So this is going to be times minus 1 minus delta kt. And all of this is multiplied by pt plus 1. Okay. And then we have another one here. So we also have minus I screwed up my parenthesis, I apologize. So let's not close this parenthesis. Let's put the pt plus 1 here, because this parenthesis here will go with the beta, okay? And this parenthesis will go with the lambda. It's really important to track our parenthesis. So inside the lambda part, the lambda t plus 1 part, we have another kt. So we're going to have minus rt plus 1 kt. So now close parenthesis on lambda, close parenthesis on beta. And this is the simplified Lagrangian. These are the non-zero terms when we do this derivative. Okay? So that's a little bit off the screen, I apologize. If you can get to here, you can probably do the problem. Okay, but admittedly, it can be difficult to get to here. So you have to be organized. You have to pay attention to your parentheses. And then from there, it's just doing the derivative, which is pretty easy. So let's do this derivative. Okay, derivative of the first part, we're going to get minus lambda t pt. And then on the second part, we're going to have, in this first thing, we have minus, so we're going to have minus lambda t plus 1, minus 1 minus delta pt. So we're going to have plus beta 1 minus delta pt plus 1, lambda t plus 1, pt plus 1, lambda t plus 1. So I multiply this into here. Then I also need to multiply this into here, right? Because the parentheses wrap around both terms. So this is also here. So we're also going to have plus lambda t plus 1, rt plus 1 equals 0. Okay, this is our first order condition for kt. So I'll put that in the box. We'll write this as lambda t pt is equal to beta, there should be a beta here too because that distributes through, beta lambda t plus 1, open parenthesis, 1 minus delta pt plus 1 plus rt plus 1. Okay, there you go. So these are our 3 first order conditions from the household. So hopefully you can get all of these. In the next video, we'll look at how to put these together to get something that's economically meaningful. Okay, so I'll see you there.